Thanks for joining us today. My name is James. I'm a material scientist and the Chief Executive here at Plastometrex. We are a technology company based in Cambridge developing novel mechanical testing systems. And today is the first in a series of short duration videos about materials, mechanics and mechanical testing. Today we're going to talk a little bit about stress-strain curves and their primary features. Stress-strain curves are important because they tell us something about the stiffness and the strength of materials. And it's essential that we understand something about these characteristics in order to design and build structures and components that are safe and fit for purpose. Let's now take a look at a tensile test taking place. The one shown in the video is of a test being conducted on a specimen of copper. But what we're also showing is the evolution of stress in the sample as a function of the imposed strain in both true and nominal forms. Now that the test is finished, let's take a look at some of the primary features of these curves. First off, the yield stress, which has been highlighted here, which corresponds to the stress at the onset of plastic deformation. Note though that the value of the yield stress is the same, whether it's been calculated in true or nominal form. If we then follow the nominal stress strain curve, we see evidence of some work hardening, but we also see that there's a peak corresponding to the ultimate tensile strength of the material. But this peak also corresponds to the stress at which necking in the specimen begins. It's useful now to compare the nominal curve to the true curve. And we see here also some evidence of work hardening. Although if we look closely, we can see that the rate of work hardening is dropping off. But importantly, what we don't see is a peak in the curve, nor will we, which means that we cannot get the UTS, or the ultimate tensile strength, from the true stress-strain curve. This is always from the nominal stress-strain curve. The final feature I'd like to draw your attention to on the nominal stress-strain curve is the point at which the material fractures. This is often called the elongation to failure, or more commonly, the ductility. Now we talk in a little bit more detail about ductility in a follow-on video where some of the misconceptions around this value and its engineering utility are discussed in more depth.